All right, so today we're going to walk through these reactions with these aromatics, the different substitution, addition reactions. And in a sense, they're like substitution reactions because you are taking off a hydrogen and then replacing it with some other functional group. But you can't do substitution on a sp2 carbon. So it's really more like an addition followed by elimination. All right, so today we're going to start talking about electrophilic aromatic substitution. So in this case, let me go ahead and cut this out and then I'll paste it on another page. All right, so still 11. All right, so with electrophilic aromatic substitution, right, the ring is actually acting as a nucleophile. Hopefully you had a chance to watch the videos I sent over the weekend. So the ring is going to be my nucleophile. And so that's why it's called electrophilic aromatic substitution, because I'm adding some electrophile to the aromatic ring. All right, again, we talked about this already, and I'll mention it again. Benzene by itself is unreactive, right? It will not react. So you have to have a catalyst present. You have to have a catalyst present in order for this to work. Right, so all of these reactions really follow the same type of mechanistic pathway, right? You have a catalyst. That catalyst activates your electrophile, and then your electrophile gets attacked by the ring, and you reestablish aromaticity. So it's really the same 3 steps. It's just different. You're going to just be working with different substrates. Let me move this down. So right, so the mechanism is really general. You have catalyst activation, of your electrophile. Then you have the ring attacks your electrophile. And then the final step is always going to be, that's the elimination part. It'll be to reestablish aromaticity. So all these reactions happen the same way. The first part of the mechanism is to activate your electrophile. The second part is for the ring to attack it. And then the third part is to reestablish aromaticity. You don't want to lose that because you lose a lot of energy by breaking up that aromaticity. All right, so let's look at that first reaction. Let's see how much room I got. I'll start another page. Let's look at the first reaction. I'll just cut it from up here. which is a halogenation reaction. Right? So you can see in this reaction, you add Br2, right? Bromine in the presence of iron 3 bromide, and you end up with a bromine on the ring, right? Notice the aromaticity is still intact, which is a hallmark of these reactions. You never lose that aromaticity. All right, so in the first step of this reaction, right, your bromine is going to be activated. So it has lone pairs of electrons that can actually make a complex with iron. So when you add in right, you can actually make a complex with that. Right. So that complexation happens with iron because iron has empty d orbitals that bromine can donate a pair of electrons to. So this is the complex that will be attacked by your ring. So that's going to get attacked by the aromatic ring. Which happens in the next step. All right, so that's the first step, and then second step is going to be let's copy this from up here. Get this right. All right, so here's your aromatic system, and let me go ahead and say up front, right here on all these carbons, excuse me, there's one hydrogen. All right, so I'm gonna put the hydrogens in, just so we don't lose that when it's time for that elimination step. All right, so I'm going to attack like that. And let me do this too, because with that complex, this bond is coordinate covalent, right? It's not really. Morning, how you doing? That's fine. Sorry. I'll cut that out before I put it on YouTube. So this is a coordinate covalent bond, right? With that bromine. It's not fully covalent. It's just the electrons are donated into that d orbital, but it's not a fully covalent bond. So let me say that too. So that's a coordinate covalent bond. And then down here is where it will become fully covalent. All right. So you're going to lose that, break that bond between the two bromines, and you end up with a aromatic intermediate that looks, well, not aromatic, but an intermediate that looks like this. Can anybody tell me what the name of that intermediate is?
It starts with an O. It's like oxanon. I don't know how to say it.
It's called a rhenium ion. And that's a common intermediate to all aromatic substitution reactions. All right. And again, whenever you see that ending, the IUM ending, that means that you're dealing with something that's positive, like a cation. So it's an rhenium ion, and that is your intermediate that gets re-aromatized. So I'm just going to steal it. And this is now negative. All right. So that iron tetrabromide is going to be, it's going to act as a base, and that's what's going to facilitate that re-aromatization. So that's that. And this is here. That's positive. This is negative, so you're going to get a pair of electrons from that. Just like that, to do that elimination. And then your aromatic system is intact again, which is good, right? You don't want to lose that aromaticity and lose all that good energy. So my bromine is attached, and you end up with some HBr, and the catalyst gets regenerated. Right? Anytime you use a catalyst, it never gets used up. Now it can stop working over time, because every catalyst has a certain number of what we call turnovers. You can measure the turnover numbers. That's the number of times it goes through and catalyzes a reaction. But any reaction that uses a catalyst is going to be, you're going to regenerate the catalyst at the end. All right, always regenerate. And some catalysts have higher turnover numbers than others for certain types of reactions, but the turnover number is just the number of times that the catalyst can catalyze a reaction. Shrink that down some. Right, so the number of times it goes through the catalytic cycle, that's what you call a turnover number. All right, so all of these reactions are basically going to have this same type of mechanism. The difference is going to be what the intermediate, what the activated electrophile complex looks like. It's going to be different for the rest of these. So this halogenation is just one reaction. All right, but all of these reactions have they follow a similar pathway where you activate and then you attack and then you re-aromatize. All right, let's do the alkylation. So alkylation is next, isolation. Alkylation. Yeah, let's do alkylation, and then we'll do another example. Give me 1 second. All right, anybody have any questions about halogenation before we move to the next reaction?
I have a question.
Whoa.
Does it matter which side that the ring is on for any of these reactions?
No,
The aromatic ring? Okay.
no, that's all semantical. It's just to help the electrons to flow better,
And then
on paper.
okay.
Mhm.
And then as far as like the double bond, how that the first step one, does it matter which double bond that we use?
Nope. They're
Okay.
all equally susceptible unless the ring is substituted. If the ring is substituted, then only certain spots on the ring will be activated for reaction. We're going to talk about that in a little bit. So
Okay.
if the ring is substituted, then it's activated at certain positions and deactivated at other positions. But if it's unsubstituted, like this ring right here, everything is fair game.
Thank you.
Mm-hmm. All right, so let's take the alkylation reaction. All right, and this is a name reaction. It's called still got it. That's all right. Let me put just so you know that's not part of reaction. Because I don't want you to look at that later and be like, oh, where does random oxygen come from? So that's not a part of reaction. In fact, I might as well just block the whole thing out. All right. So the Friedel-Crafts alkylation is exactly what it says. You are adding an alkyl group. You add an alkyl group to the ring. So you normally start with some type of alkyl halide. You can actually add primary alkyl halides. So you can add something like something like this, where this is bromine or iodine. And your catalyst in this case is an aluminum catalyst, right? Aluminum trichloride. Very, very similar mechanism. The only difference is the activation step. In the activation step, you actually get a carbocation. So primary alkyl halides. They don't work as well simply because you do get a carbocation. I'll just say that they're not as reactive. So let's go through the mechanism here. So here we're going to start with step one, which is the activation of your electrophile. So we're going to start with something different. I'm going to start with something like this. All right, so I'll start with this tertiary. alpha halide, and then I'm going to react that or add that aluminum trichloride catalyst, right? So in this case, right, I'm going to end up with an aluminum complex. Make that. All right, so you coordinate first. All right, so that's a coordinate covalent bond. And then you lose your halogen. All right, so you end up with a carbocation like so. And this is negative, right? So then it's the carbocation that gets attacked in the second step. And again, because the ring is not substituted, all three of those double bonds in the ring are equally reactive. And I'm gonna turn this way so you can see what happens. This is just gonna come here and attack like that. And then you're gonna get that rhenium ion intermediate. I screwed all that up, my bad. So now there's a plus charge here. All right. And then it's that rhenium ion intermediate that's going to be deprotonated using the aluminum tetrachloride. This is negative. You got a hydrogen here that you're going to pull off and eliminate. To reestablish that aromaticity. Right, and then your catalyst again always gets regenerated. Right, so the Friedel-Crafts alkylation, let me show you an example because we got an example down here we can work through. Where is it? Right here, yeah. Let's work through this example right here. Because it says if Friedel-Crafts is carried out on a primary alpha halide, sometimes you get unexpected products, right? So it says propose a mechanism. So let's look at let's just go through the mechanism. What's the first step? What's the first thing that's going to happen?
Do you have to activate the bromine?
Mm-hmm. I'm going to take that. Make sure I got it. That's 5 carbons total. So here's my bromine. I'm going to activate that by complexing it with iron bromide. All right, so I'm attacking here, we're donating, and electrons here. Right? So then when that happens and you lose this bromine, what are we going to end up with? And why is it problematic? What's wrong with that carbocation that we made? Remember, for carbocations, y'all remember the trend? Like,
Yes.
yeah, so when I lost that bromine, I actually made there's a actually a CH2 here at the end of this line, right? That's a primary carbocation. That's horrible, right? A lot of times when you have primary carbocations and they're in the presence of other groups, right? What's one way to stabilize it? A primary carbocation. And that, to help you think about that, look at the product that we got. All right, so what can we do to stabilize that primary carbocation? Can we move it? Can we move the carbocation somewhere else? Do we have a site that's more suitable to be a carbocation? Let me ask that question. In this molecule.
Yeah. Are we trying to make it? We're trying to make it a more stable
Yes.
carbocation, correct?
Yes.
So we're that tertiary.
Okay, I'm with you. So how can we do that? Right, there's something that's definitely we have an out, like we have a way out. It's just a matter of remembering what it is, right? So when you have a primary carbocation, that a lot of times you get rearrangements that can happen.
Can we do red?
No, we can't do resonance because there's no donor, but we can do a hydride shift, which is a type of rearrangement, right? There are other rearrangements that stabilize carbocations, methyl shifts. Right, where you move right, you can move a methyl group or you can move a hydride. In this case, we have a hydrogen that can shift over to here. All right, so if we do a hydride shift, let me move this out of the way. If we do the hydride shift, that's going to put the carbocation on that tertiary site. Here. And it's going to move that hydrogen down to here. Right, the hydride shift is the the hydrogen and both of its electrons. That whole bond is going to shift over to where that carbocation is. Right, in this case, this would be a 1,3 hydride shift. Right, because if you start here, right, that hydrogen is on the third carbon, so we just call it a 1,3 shift. You can do a 1,2 shift, a 1,3 shift. It just depends on where the carbocation is and where the hydrogen is that's going to move. Right, if you did a 1,2 shift, you would get a secondary, but doing the 1,3 shift gives you a tertiary carbocation, which is infinitely more stable than a primary.
So Dr. Russell, anytime we have a carbocation, a primary carbocation, we need to do some type of shift in order to make it a more stable carbocation.
Yeah, more than likely, you in practice, it'll happen. Like there's nothing you can do about it. If you have an intermediate that ends up being a primary carbocation, which is very unstable, I hate to, well, I'll say it like this: the universe will do what it has to do. So in practice, you really can't stop it. That's why I worded the question like I worded it, that unexpected products are formed. You expect the ring to attack that primary carbon, but in reality, what you're going to end up with is the ring attacking the tertiary cation, right after the rearrangement happens. Right, but so I mean, on paper, yes, you may have to show the rearrangement, but in practice, it's going to happen anyway. Because those primary carbocations just are not very stable, and so if there's a way to stabilize it, it's going to happen. Move that up. So that is what gets attacked in step 2 by the ring. I'm gonna just combine steps 2 and 3. So it's the ring here attacking the tertiary. Make sure I've got my double bonds in the right place. That's the carbocation that gets attacked. I'm putting that here. And the plus charge is now here on the ring. And then my aluminum, fix that up. It's horrible. The aluminum tetrachloride is just going to come in and do what it does, right? To reestablish that aromaticity. So we started with iron, my bad. Not aluminum. All right, so with the Friedel-Crafts alkylation, like sometimes depending on what type of alkyl halide you use, that alkyl halide is going to end up rearranging once you get to the intermediate. Right, so that's why I said up top that primary alkyl halides are not really suitable just for this reason. Because if that's the product you're trying to get, you need a different way to do that. Let me ask this question. If I had a primary alkyl halide, what if I wanted to make this product? How can I make it? I'll buy you lunch if you tell me right now. And it's not a reaction that you don't know. Think about it. Think about something we've already done, where you won't have to have the danger of rearrangement happening, giving you some product that you can't use. This is why it's important to understand synthesis and to understand that you need more than one tool in your toolbox, because every reaction, every substrate is not amenable to every reaction. So sometimes you have to have a different pathway to get to something. How can we make that?
Garage door.
The first person to tell me I'm buying you lunch, and anybody who I've ever done that for, they can tell you I'm good for it. It's legit.
I know this doesn't count. It's definitely not the full answer. Maybe this will help somebody else. I just remember that SN2 like prefers primary carbocations, but that's
Okay, but okay, but can we do that with an aromatic substrate? If I'm saying if we had to start from this alkyl halide. Now I agree with your rationale, because you could do like a benzylic substrate with some a benzylic nucleophile. I agree with that. But I'm talking about if we had to start from this. Now, if we did a SN2, you're right, we could do this.
Garage door.
Do something.
Could we do a Gilman? Oh wait, hold on.
Come on with the come on.
Could we?
Trying to get that lunch, get it. It's on the table. The money is there.
Could we do the? I'm gonna say the Gilman reagent. So
Yes, we could.
for real?
Yeah, that's what I'm getting at. We could use the organometallic method and do a coupling reaction, and we don't have to worry about any type of rearrangement because there's no intermediates. There's no carbocation intermediates.
Right.
If we did an SN2 type T, we would have to think about this carbon right here being your nucleophile, and then you have to use a different electrophile. So we have to use this instead. Let me see. Let me take one carbon out. So we have to use this instead. Yeah, and then put the bromine here, and then put those two together. So yeah, we could do that. But that's not the substrate that we wanted to start with. I want to start with what the original substrate was. See, this is why I love teaching, because you get to go down rabbit holes and then come back to the same topic. All right, so if we did an SN2, it would have to be this, but we want to use this. So who was that? You, Logwood?
Yes, sir.
All right, so you're saying, and I'm actually gonna buy both of y'all lunch, because at least that both of these are plausible. But what I wanted was to use this substrate that we have up top. So if we did a Grignard, so we start with this, or Gilman. So we can start with that. Is that right?
Yep.
Start with that plus our substrate that we had. Come on, Russell, get it right. Like that? Absolutely, we could couple those two together and get the product that we want.
Cool.
That
That
plus, see, I'm just gonna put pH because you got one left. Right? Absolutely.
Dr. Russell, could you zoom out a little bit?
I will. I'm just trying to make sure that the further I zoom out, the worse my handwriting gets. So I have to zoom in so I can write halfway decent. I'll zoom back out.
Okay.
So this is a substitution method, and then this is an organometallic method. Nice work, both of you.
Thanks.
Go ahead and put your cash out. Both of you put your cash app in the chat. Right? But see, this is the beauty of chemistry, right? You always got, like the old people used to say, more than one way to skin a cat. There are always multiple routes to get to a specific target. That's why it's so important to know all of your different, you ain't gonna know all of them, but to have a basis of knowledge about how to make certain types of bonds, right? And we talked about this already, that one way to make a bond to an aromatic system is to start with an organometallic and do a coupling reaction. Right? We talked about you could use a granular, aromatic granular. You could use the Gilman reagent, and you can use some type of alkyl halide to do that reaction. Right. So this is good. All right. We gotta stop because we only got a minute left, and we got one more reaction to look at before we start talking about these this nomenclature. And I'll write the question in up top here before I post it, so it won't be so esoteric when you're looking at it later. You'll know why we did this section. All right. Questions? Any questions about this? All right. So lunch is on me for y'all two folks. T, you didn't put your okay, there it is right there. All right. If there's no questions, we're gonna go ahead and stop now, and we'll pick this back up. Let me stop recording too, so they don't hear all our personal business. Yeah, we'll pick this up on Wednesday.